everyone, welcome back to Brainstorm. This is our Level 2 Algebra walkthrough series. Now, in this video, we're going to go over the second part of logarithms, which involves combining logarithms and exponents and looking at their applications. So let's jump into it. So recall the following from level 1. So if we have x raised to the power of a, and that's equal to y raised to the power of a, then because we've got the same power on both sides of the equation, this means that the bases are equal to. So this leads us to say that x is actually equal to y, and the reason for that is because equal powers, we have equal bases. And similarly, the other way around, if we've got a raised to the power of x, which is equal to a raised to the power of y, because our bases are indeed the same, this leads us to say that, well, in fact, the powers are the same, so we can in fact say x is equal to y. But for this reason, it's the opposite, so we would have equal bases, hence equal powers. And so if we look at some quick examples, if we had 81 is equal to 9 to the power of x, and we wanted to rearrange for x, how would we do this? Well, we would notice that 81 is the same as 9 raised to the power of 2, and so we would get 9 raised to the power of 2 is equal to 9 to the power of x. Now, because we've got equal bases, we've got 9 on either side of the equation, that means that we can set up a new equation, 2 is equal to x. So we've found a solution for x, which was 2. What about 3 to the power of 7 is equal to x to the power of 7? We'll notice that both the left-hand side and the right-hand side of our equation have 7 as the power. And using our first rule here, if we've got equal powers, we have equal bases. So this tells us that, in fact, 3 is equal to x. But consider the fact that, what if I put, in this first example here, what if I made this like 37 is equal to 9 to the power of x? Well, now I can't simply rewrite this as 9 to the power of something, right? Because this is not a, well, our power will not be a nice integer number, it will be some kind of decimal value, right? And so how do we get around this? Well, in fact, we can actually use logarithms to solve what this power would be. So if I clear that a little bit and I scroll down a bit, how can we use logarithms in our cases? So let's set up our equation again. Let's use the same equation. 81 is equal to 9 raised to the power of x. How can we solve this using logarithms? Well, first we need to take the log of both sides. So what I would do is I would take the log of 81, and I would take the log of 9 raised to the power of x. And you might be thinking, well, why can we do this? Let's consider just a simple equation. Let's say we had x plus 3 is equal to 4. Now we know the solution of this is actually x is equal to 1, right? Because 1 plus 3 is 4. What happens if I, let's say I multiply both sides by 6? So multiply both sides by 6, and 6 times 4 is 24. Well, if I expand this out, I get 6x plus 18 is equal to 24. Then, if I solve this now, 6x is equal to 24 minus 18, which is 6, and therefore x is equal to 1. So it doesn't matter what I do. If I do the same thing to both sides of the equations, my equation still remains valid, right? It still remains constant. And so if I clear all this working here, if I take the log of both sides, I still keep the equation the same, right? I'm not changing the value of my equation, and so I'm allowed to apply the logarithm function to both sides. Another thing to note here is that because I haven't specified the base of a log, we can assume this is log base 10, but actually it doesn't matter what the base of a log is in this case. So I've got log 81 is equal to log of 9 to the power of x. Now, if you remember from my last video, if I have some logarithm, log base b of a to the power of x, I can rewrite this as x log b with argument a. Okay, and if you're unsure of how that works, you can watch the previous video on logarithms, but I'm just going to apply that to this x up here. Right, so what we're going to get is log of 81 is equal to x multiplied by log of 9. And now I can isolate my x, right? If I divide both sides by log a, I'll get x is equal to log of 81 divided by the log of 9. Okay, and if I plug this into a calculator, which I've got one right next to me, if I solve log 81 divided by log 9, I get 2 as my answer. So x is equal to 2, and as you can see before, we've just solved for that. Now this was quite convoluted, right? It took, a few steps to solve, but this is really important because I can essentially find values of x where x is not an integer. For example, let's look at one of those kind of harder examples, like 37 is equal to 9 to the power of x. In fact, let's do a different number than 9. Let's do 4 to the power of x. If I apply my logarithm rules, I can get log of 37 is equal to log of 4 to the x. So I'm just taking log of both sides. I can move this x down, so I can get log of 37 is in fact equal to x multiplied by the log of 4. And therefore x is equal to the log of 37 divided by the log of 4. And if I solve this now, the log of 37 divided by the log of 4, I get the answer to be 2.605, right? And what that means is 4 to the power of 2.605 should give me 37, or a number close to that, because I've actually truncated this number. It's a bit longer. So if I take 4, if we check this in calculator, 4 to the power of 2.605, in fact gives me 37.014, and that's because I just rounded this number. So logarithms are actually quite a powerful tool that allow us to solve equations quite nicely. So let's look at some example questions. Question 1. If I have 3 raised to the power of 4x and I set that equal to 30, so let's solve for x. So we're just going to do exactly the same thing that we've been doing before. I'm going to take the log of both sides, so log 3 to the power of 4x is equal to the log of 30. What I mean by taking the log of both sides is I'm putting these into the argument of my logs. Okay. So now, how do I do this? Well, using our logarithm properties, I can bring the 4x out. So I get 4x multiplied by log of 3 is equal to the log of 30. And now 4x is equal to the log of 30 divided by the log of 3, right? And therefore, x is equal to the log of 30 over the log of 3 divided by 4, which is the same as multiplying by 1 over 4, which gives me log 30 divided by 4 log 3. So this is my solution for x, right? So x is equal to log 30 over 4 log 3. And that should give me a decimal, or the value of x around it should be about 0.774. So let's double check I did that correctly. So log 30 divided by 4 log 3, we get 0.774. Cool. All right, question 2. Simplify log 6 minus 2 log y. So how do we do this? And I'll give you a hint if you want to pause the video and try it yourself. We're going to do essentially the reverse of what we've been doing before. All right, so I'm going to go ahead and try and solve this. So we're just simplifying, right? And we need to remember the rule. If we've got log b a, oh sorry, let's put this as an x in fact, minus log b y, this is the same as log b of x divided by y, right? And that's from our logarithm properties from the last video. And so we can do something quite similar. We can say we're going to have log, and this is essentially base 10 of in fact, we can't do that just yet because we've got a 2 in front of our log, right? And we don't know how to deal with that yet. So that's my bad. We need to manipulate this 2 log y here. So how are we going to go about doing that? Well, remember that I can bring this, in fact, let me rewrite out the property. If I've got log b of x to the power of y, this is the same as y multiplied by log b of x. And the reverse is true as well. So I can go from this form here and bring the power back onto that x. Right, and so if I was going to apply it to this here, how would I go about it? Well, this is the same as log 6 minus log of y squared, right? And now because we've got it into this form up here, we can actually simplify it down a lot easier. So this is equal to the log base 10 of 6 over y squared. And we don't actually have to specify this base 10. We just assume that it's base 10, right? But this is our final answer. All right, let's look at question 3. Now, in question 3, what we're dealing with is a solve for x question where we have 2 log of x plus 1 is equal to log 4. So how should we go about doing this one? Now, what we need to do is recognize that if you remember, we can bring this 2 as a power of the argument of the log, right? So this is the same as log of x plus 1, and we're going to square that because we're squaring the argument to bring this 2 all the way up, and that's equal to log of 4. Okay, cool. Now let's bring this log of 4 to the left hand side, right? So hopefully we'll be able to use one of our logarithm properties to simplify our logarithms. So we're going to have log of x plus 1 squared subtracted from the log of 4 is equal to 0. And now remember that if we subtract 2 logs with the same base, and remember that the base here is log 10, or we can assume it to be log 10 at least. And so what that means is that we can actually divide the arguments. So we're going to get the log base 10 of x plus 1 squared divided by 4, and that's equal to 0. And now we need to use our snail trick, right? So we've got 10 to the power of 0 is equal to this kind of quadratic here. So 10 raised to the power of 0 is equal to x plus 1 squared over 4. Now 10 to the power of 0 is the same thing as 1. So 1 is equal to x squared plus 2x plus 1 over 4. Now let's bring the 4 up. So we get 4 is equal to x squared plus 2x plus 1. And then now we can just solve for our quadratic, right? So let's give myself some more space. So x squared plus 2x minus 3 is equal to 0. So we should be doing what multiplies to negative 3 and sum to 2. So if we have negative 3 and 1, that sums to negative 2. If I have negative 1 and 3, that should give me positive 2 and negative 3. Right, so our coupled list is 3 and negative 1, so we get x plus 3 and x minus 1 is equal to 0. This gives our solutions x is equal to negative 3 and x is equal to 1. So these are our solutions for x. Let's just have a look at where x is in our logarithms to see if x can indeed be a negative number. And so x is here. So if x was negative 3, if x is equal to negative 3, then we would have 2 log of negative 3 plus 1 is equal to log of 4. Right? And so we'd have 2 log of actually negative 2 is equal to the log of 4. But remember from our last video that, well, in fact, the argument of a logarithm can never be negative. And so negative 3 is not a valid answer, and so x can only be equal to 1 for our logarithm. That was a bit of a tricky question. Alright, and let's look at the final question before we move on to something else, which is Q4. Let's consider the following equation. Consider the following equation. Right, and that equation is going to be a raised to the power of x is equal to q, where q belongs to the natural numbers. Now, if you don't know what that means, all I'm saying is that this value q must take on the value from 1, it could be 2, it could be 3, all the way until infinity, right? So it has to be a positive counting number. Now, what we want to do is we're going to rearrange for x. So let's rearrange for x. And we also need to explain why x can never be 0. So explain why x cannot be equal to 0. So we need to rearrange for x. So how are we going to do that? Well, we're going to use our logarithms, right? So we're going to have log of a to the power of x is equal to the log of q, because we take the logarithm of both sides. And then I can bring this x out. So x multiplied by the log of a is equal to the log of q. And so now x is equal to the log of q divided by the log of a. And remember, this is technically, we can assume it to be base 10. So we've now rearranged for x. We've done that first part, but now we need to explain why the value of, not why the value of x, but we need to explain why the value of a can never be 0. So why can the value of a never be 0? Well, if you look at our value of x, we're having a log q over log a. So we're dealing with this log 10a. Remember that the argument of a log must always be positive, right? Let's write that down. The argument of a log must be positive. In other words, a must belong to the natural numbers too, right? Because a must be a positive number. And so what that means is that hence a must be greater than or equal to 1, and therefore a cannot be equal to 0. So that is our second part here. Alright, next we're going to look at something called compound interest. Now, compound interest is the interest calculated on the initial principal of a deposit added with the accumulated interest from prior periods on said deposit. And it might be easier to think of this as interest on interest, since that's a lot of words. But we don't really need to understand too much about compound interest. I'll just draw out a graph here, right? So this is my axis here, and on the y-axis we've got money, and on the x-axis we've got time. Okay, and what we're saying is that compound interest looks something like this, right? So it's a nice exponential curve, and we'll call that compound interest. And well, if we have a straight line, this is something called simple interest, right? So interest that's not compounding, okay, or that's just always done on the initial principal. That's called simple interest. Compound interest is like compounding on the sum added with the already earned interest every time, if that kind of makes a bit more sense. Okay, but the thing that we want to notice here is that this compound interest curve is actually an exponential. And because it's an exponential, we can use logarithms on it. And so compound interest is a pretty heavily used topic within the exams because it's heavily related to logarithms. Now, the general compound interest formula looks like this. It's a is equal to p multiplied by 1 plus r raised to the t. Now let's go over through what the different variables mean. So a is the total amount. P is our principal, or our initial investment. Principal / initial investment. Right. R is our interest rate. And T stands for time. Okay, and so if we wanted to rearrange this equation for A or P, it's pretty trivial, right? We just have to divide and do some simple rearranging. But what about for R and T? It's not as simple, right? And so I'll show you how to derive it for this general formula, but in your exams you might have to do something a bit more complicated, and that's alright. It will be following the exact same steps, just with maybe an extra a few constants in there. Okay, now if we want to rearrange this for t, we need to essentially use logarithms. So how are we going to do that? Well, first, notice that this is a constant, so we're going to divide that out on both sides. So we're going to get a over p is equal to 1 plus r raised to the power of t. All right, and so now we're going to use our logarithm. So we're going to apply the logarithm function to both sides. So the log of a over p is equal to the log of 1 plus r to the power of t. Right, and then I can bring this t out, right? So the log of a over p is equal to t multiplied by the log of 1 plus r. Okay, and then now t can be isolated easily by dividing log of 1 plus r on both sides. So the log of a over p divided by the log of 1 plus r is actually equal to the value of t. So rearranging for our interest rate, and I'll rewrite our equation. So our original equation is a is equal to p multiplied by 1 plus r to the power of t, and we want to rearrange for this thing in here. Now, taking logarithms isn't going to be helpful, because if I do the same steps as up here, you'll see that my r becomes trapped inside a log, and so that's not very useful. So we actually don't need to do anything with logarithms, we just need to know our exponent rules. So first I'm going to divide both sides by p. So a over p is equal to 1 plus r to the power of t, right? And now I can, if this t was at 2, for example, so if this was 1 plus r squared, to get rid of the square, I would take the square root of both sides. And so what I can do is I can take the tth root of both sides, right? Because it doesn't matter what this value of t is. If a t was like 3, for example, I could take the cube root, or I could take the 4th root, or the 6th root, or the 100th root, right? It doesn't matter what t is. I can still take the tth root, right? That makes sense. So let's take the tth root of both sides. So the root of t of a over p is equal to 1 plus r. Now I just subtract both sides by this 1 to isolate the r. So r is equal to the tth root of a over p minus 1, and this is fully rearranged. Alright, and finally, we'll look at some exam question from the 2018 paper. So, interest is compounded on a principal investment at the end of each year. If the total amount of the investment after n years is $8, then they give us a is equal to p multiplied by 1 plus r over 100 to the power of n, which looks pretty similar to something we've just done, and r is the interest rate per year. Now, we've got Anushka here, and she's investing $20,000 at an interest rate of 3.85%. And they've even simplified this equation down for us here. How many years will it take for her investment to be worth $25,000? Okay, so how do we go about doing this? So we want to know when the value of A, or the total amount, is $25,000, we want to work out the value of N. So let's rearrange, let's substitute. So 25,000 is equal to P. Our principal investment is actually 20,000. 20,000 multiplied by 1.0385 to the power of N. And we want to solve for N. So how do we do that? Well, remember, if we're rearranging for time, we need to take the logarithms. So how do we do that? Well, first of all, I can even, in fact, it might be easier if I divide both sides by 20,000 first. So 25,000 over 20,000 is equal to 1.0385 to the power of N. If I take the log of both sides, so the log of 25 over 20 is equal to the log of 1.0385 raised to the power of N. I can bring that N down, so this is the same as the log of 25 over 20 is equal to N multiplied by log multiplied by 1.0, well, not multiply, but the log of 1.0385. I'm running out of space here. So N is equal to the log of 25 over 20 divided by the log of 1.0385. And if I now put this into a calculator, I should be able to get the value of N. So log of 25 over 20 divided by the log of 1.0385 and I get 4.26 years. I hope that's the right answer. I don't have the mark schedule here, so we'll just move on. Now, in this next part, we've got Samisi, who's investing his money at a different rate, a different interest rate than Anushka's investment. And now his investment doubles in value after 12 years. So what is the interest rate for Samisi's investment? So let's say go A is equal to P, 1 plus R over 100 to the power of N. So we want to work out the value of R. We know that the value of N is 12. So A is equal to P multiplied by 1 plus R over 100 to the power of 12. So what's the value of A and P? Well, we actually don't know. But we do know that his investment doubles in value after 12 years, right? So whatever the value of P is, the value of A is twice that. So this is just a ratio, right? We're saying this is 2 to 1, but we don't have to write it like this. We could rewrite this as 2P is equal to P, because whatever his principal was, we're earning twice that in 12 years, multiplied by 1 plus R over 100 to the power of 12. Now, because we're rearranging for R, let's bring this P over to the left side. So 2P over P is equal to 1 plus R over 100 to the power of 12. Our P's cancel, so we're left with a 2 on the left-hand side. Now, because we've got a 12 here, we're going to take the 12th root of both sides, right? So the 12th root of 2 is equal to 1 plus R over 100, because the 12 here will cancel out. So, what do we have here now? Let's subtract 1 from both sides. So, the 12th root of 2 minus 1 is equal to R over 100. And so, R is equal to 100 multiplied by 12, the 12th root of 2 minus 1. And I've got a calculator here, so let me calculate the 12th root of 2. Minus 1 multiplied by 100, and the interest rate is 5.946. I imagine it's percent, right? Yes. So hopefully I've got that correct. But that's it for this video on logarithms. Thanks for tuning in, and next time we'll be taking a look at quadratics.